Hello everybody, my name is Renzheng. Here I'm going to present our work called DeepHunter, a graph neural network based approach for robust cyber threat hunting. Threat hunting is a proactive search for intruders who are lurking undetected in the organizational information system. It is increasingly becoming an important component to mitigate the APTs. The goal of threat hunting is to match audit logs against known adversarial behaviors. The typical workflow of threat hunting is shown in the below figure. First, using the graph to represent carrier relations in the audit logs, which is called the provenance graphs. Based on the provenance graphs, some typical tasks of a threat hunter include provenance triage, which aims at filtering the suspicious paths from the provenance graph. Second, alert correlation, which correlate alerts generated by detectors. And third, threat investigation, which finds the attack behaviors in the provenance graphs. Existing threat hunting methods include nodos, which finds attack paths on the provenance graphs, rapsheet, which correlates alerts according to the provenance graph, and parrot, which aligns the query graph with the provenance graph. These methods have indeed improved the threat hunting abilities. However, these methods rely on the complete provenance graph. In practice, the provenance graph may miss some attack events, and real attack activities recorded in the provenance data are not completely consistent with the known attack behaviors due to auditing systems, attack mutations, and random noise. So the problem that our paper tried to solve is how to achieve robust threat hunting. Now let's see a motivating example of our paper. The known attack behavior is that at first, the attacker first employs the eternal blue to establish a foothold. Then he modifies the Windows registry for persistence. At last, the cryptocurrency miner is started. However, the persistence techniques is changed in the real attack scenario, which uses WMI for persistence. The query graph of this scenario is shown below. In our paper, we use the query graph to search the audit logs which has recorded the persistence while WMI. Note that the real attack provenance graphs are disconnected, which would impair the performance of path-based methods, but our approach is robust against it. The key idea of our paper is that we treat the threat hunting task as the graph pattern matching problem, and we design a GAN-based model that are resistant to the inconsistencies. If both the node attributes and the graph structures in the query graph are largely matched in the provenance graphs, the model output 1. Otherwise, it output 0. The GAN-based model has two advantages. First, the graph neural networks naturally excel at efficiency, since modern GPUs can largely accelerate matrix computations by parallel processing. Second, no additional expert knowledge about attacks and the target system is needed, as the graph neural network is trained in an end-to-end manner. However, designing the GAN-based graph pattern matching model has two challenges. First, how to represent node attribute information effectively. There are multiple node types in graphs. Each node has many attributes, and different attributes may have different importance to the graph pattern matching task. Second, how to represent graph structures effectively. The query graph is small and noise-free. The provenance graph is bigger and contains redundant nodes. So when these two graphs represent the same behavior, how to make their representations closer in vector space? Now, let's look at our solution DeepHunter. It consists of two branches. The upper branch deals with threat intelligence information, and the lower one is for the audit logs. We manually construct the query graph from the attack report and construct the provenance graph from audit logs. Both of them are fed into our GNN-based models. The model contains two parts, which are used to represent node attributes and graph structure. The outputs of two branches are the vector representation of two graphs. We employ NTA model to learn their relations. When the query graph and the provenance graph represent the same behavior, the output is 1. Otherwise, output is 0. Next, we introduce our attribute embedding network. We first generate an embedding for each attribute of the node, and then we compute the node's input feature by aggregating the node's attribute embeddings. The attribute embedding generation. It contains two steps. First, we translate a path on the provenance graph as a sentence. Then, we adopt the NLP model word-to-vector to obtain the vector representation for each attribute. Then, for the attribute embedding network, the goal of the attribute embedding network is to obtain the input features of each model, which incorporate node's attribute information. We represent a node's input feature as the aggregation of its attributing embeddings. Common aggregation functions include sum and average, but for the graph pattern matching task, the importance of each node attribute may be different. Hence, we use the attention mechanism to learn the weight for each attribute of a node. Now we introduce the graph embedding network, which is used to represent graph structures of both the query graph and the provenance graph. There are two stages in the graph embedding networks: the node level embedding stage and the graph level embedding stage. In order to model two graphs with distinctive characteristics, we use two different graph embedding networks to encode the provenance graph and the query graph respectively. It is the node embedding method that leads to the difference between the query graph embedding network and the provenance graph embedding network. We adopt the existing GCN to embed the nodes in the query graph. To represent the nodes in the provenance graphs, we design a provenance graph embedding network, which is capable of dealing with the redundant nodes while remaining the key information for matching the query graph. The typical GNN layer is the attention aggregator, which could aggregate information from neighbors for the target node. Note that for a node in the provenance graph, different neighbors may have different importance for graph matching. In particular, the redundant neighbors should be assigned a lower importance value to reduce their impact, while the nodes that can match the corresponding ones in the query graph should be assigned a higher importance value. For this purpose, we adopt another attention mechanism that can learn weights for neighbors of the target node. Now we obtain the node embedding for each node in both the query graph and the provenance graphs. How to generate a low-dimensional embedding vectors for a graph using node embeddings. We adapt the provenance graph embedding in SimJNN. Specifically, SimJNN believes that two graphs with different size should not be familiar, but that's not true in the thread hunting task. So we replace the sigmoid function in SimJNN with the softmax function, and the final graph level embedding is represented as below. The implementation part. In practice, due to hosting long-term system logs is prohibitively expensive, analysts attempt to reduce the provenance graph and yet preserve the quality of thread hunting. Before feeding the original provenance graphs into our model, we prune the provenance graph. We first generate suspicious events. Then, based on them, we prune the provenance graph using a graph reduction algorithm. This graph reduction algorithm is basically an adapted BFS algorithm, which keeps the suspicious events. Next, we generate the training samples for learning our model. The query graph can be considered as summarization of its corresponding provenance graph. Therefore, we use the graph summarization techniques to generate the matched query graph for each provenance graph. We also add random noise to improve the robustness. The details are illustrated in the paper. To evaluate the efficacy of DeepHunter, we utilize provenance data which contain 5 APT attack scenarios, including 3 real-life APT, which are from DARPA-TC engagement, and 2 synthetic APTs. For each of the attack scenarios, the corresponding query graph is also provided. We chose 5 scenarios with different degree of the inconsistency between the query graph and the corresponding provenance graph. We define 3 inconsistency scores to quantify the degree of the inconsistency. These are missing nodes and paths in the provenance graph and the GED distance between the query graph and the provenance graph. The inconsistency scores are shown in the table. The dataset summary is shown in the below table. We compare DeepHunter with Parrot and other GNN-based graph matching models. In this figure, we can see that all matching scores calculated by DeepHunter are greater than the threshold, which is 0.5. This result shows that the accuracy of DeepHunter can be guaranteed in scenarios where there exist various degrees of the inconsistency. Moreover, as the degree of the inconsistency increase, all matching scores decrease, but the curve of DeepHunter is more stable. On the contrary, the curve of Parrot drops faster than the GNN-based graph matching models. Even worse, the matching score calculated by Parrot is less than its threshold. In the most inconsistent scenario, Q5 plus ETW, which means that Parrot fails to identify this attack. We also detail the false positive results of DeepHunter and Parrot in this table. The result can demonstrate that the high robustness of DeepHunter is not built upon false positives. Finally, we compare DeepHunter with a non-learning graph matching approach, which is WL kernel and other GNN-based graph matching models. Note that these GNN-based models are not specifically designed for thread hunting. We evaluate all the graph matching approaches using the AUC value. We can see that the performance of DeepHunter is superior to other approach. That's all. Thanks for your time.